You can have a perfect deployment pipeline, green unit tests, and still watch your system violently self-destruct the moment it hits production. As software projects approach release deadlines, engineering teams chase a specific ideal, a zero-defect sprint. The assumption is that with enough testing, every flaw can be found and fixed before shipping. But the number of potential input combinations and internal logic paths in even a moderately complex application quickly exceeds the number of atoms in the universe. Exhaustive testing is a mathematical impossibility. This presents a structural dilemma. If 100% test coverage is a mathematical myth, why do certain organizations consistently release resilient systems, while others push flawless continuous integration pipelines that result in catastrophic outages? The 1999 launch of NASA's Mars Climate Orbiter provides a stark illustration of this gap. This $125 million mission shows how flawless internal testing often fails to account for the actual operational reality of a complex system. Building elite engineering organizations requires abandoning the pursuit of zero bugs. Instead, teams must build their architecture around risk management, aggressive boundary validation, and immediate feedback loops. To understand how systems actually fail, we have to isolate the difference between verification and validation. Verification is an internal technical check. It asks, are we building the product right? Meaning, does the code match the written specifications? Lockheed Martin engineered the thrust modules for the Mars orbiter. Against their own local requirements, their engineers passed P3 internal verification test. Validation, however, is the external operational check. It asks, are we building the right product? Does the system survive and function in its actual end-to-end environment? This animated diagram illustrates the critical data handoff. Lockheed Martin transmitted thrust data in imperial units, pound-seconds. NASA's navigation software expected metric units, newton-seconds. Both engineering teams produced modules that operated flawlessly in isolation, but when integrated in the vacuum of space, the mismatched data caused the spacecraft to descend too low and disintegrate in the Martian atmosphere. The International Software Testing Qualifications Board defines this exact scenario as the absence of errors fallacy. Reducing internal code errors to absolute zero has no technical value if the finished system fails to satisfy its operational requirements or deliver its intended business outcome. Isolated unit tests verify specific modules, but they cannot validate how those modules interact with the messy reality of a production environment. Modern software teams bridge this gap through shift-right testing, validating code in the actual production environment, and canary deployments, where small percentages of live traffic reveal integration failures before they can impact the entire user base. Since testing every possible logic path is mathematically impossible, engineering teams have to prioritize their resources through risk-based testing. Decades of software research by IBM and Capers-Jones reveal a strict pattern of failure, governed by the Pareto principle. This heat map visualizes that reality. Consistently, roughly 80% of all defects are concentrated in just 20% of the system's modules, typically areas with high cyclomatic complexity or heavy legacy modifications. Running an automated regression suite that reports a 100% pass rate every day creates a dangerous illusion of system health. This triggers what the ISTQB calls the pesticide paradox. As the source code mutates and expands, running the exact same test scripts repeatedly eventually fails to detect any new vulnerabilities. To prevent this stagnation, teams use mutation testing.
It measures the actual quality and strictness of the test suite, rather than just tallying the sheer volume of code lines covered. The process deliberately injects synthetic faults, mutants, into the source code. If the existing test suite does not fail when it hits the synthetic bug, the test itself is proven defective. A continuously green deployment pipeline only proves your code hasn't broken old logic patterns. It does not mean the system is secure against new layers of complexity. The most common friction in software engineering occurs when a tester logs a defect, only for the developer to reply that it works perfectly on their local machine. This friction stems from blurred operational boundaries. Testing is an active process of discovery, deliberately causing a system to fail. Debugging is the subsequent engineering process of tracking down the location of that failure and repairing the code. To trace how these failures escalate, we follow a strict 4-step causal chain. It starts with an error. An error is inherently human. It is a cognitive bias, a mistake, or a developer's misunderstanding of the initial business requirements. That human mistake becomes a defect. This is the latent vulnerability embedded directly into the code logic, like an incorrect point limit threshold sitting silently in the backend. The defect only triggers a failure when the software executes in production and a user action hits that dormant code incident. Applying a hotfix to that single line of code stops the immediate bleeding, but it leaves the systemic flaw completely untouched. This requires root cause analysis. By asking a series of whys, we trace the runtime failure backward to its exact procedural origin, often discovering that the developer wrote the wrong code because the initial documentation was flawed. Patching a bug keeps the software running for today. Exposing the root cause repairs the engineering culture for tomorrow. The separation between isolated bugs and systemic flaws is the difference between quality control and quality assurance. Quality control is a corrective, product-oriented execution. It is the physical act of finding existing bugs in the source code. Quality assurance is entirely different. It is a preventive, process-oriented framework designed to ensure those bugs are never authored in the first place. We measure the maturity of these QA frameworks using 2 strict metrics: Defect Removal Efficiency, or DRE, and the escape rate. This table compares organizational performance across both factors. The industry average team operates with an 85% DRE, meaning 15% of defects reach production. By contrast, elite organizations push DRE past 99%, reducing their escape rate to under 1%. Elite teams do not achieve this variance by hiring a massive army of manual testers. They achieve it by utilizing their raw defect data to continuously upgrade their QA processes. They recognize that a massive production outage is rarely the fault of a single reckless developer. It is more often a predictable consequence of an ambiguous project requirements document. To prevent this, these organizations institute the shift-left methodology. This pulls quality assurance out of the release phase and forces it directly into the earliest planning stages. Practically, this means instituting formal reviews, like the 3 Amigos meeting, where the product owner, lead developer, and QA engineer define the exact edge cases before a single line of code is written. The pursuit of a mathematically perfect zero-bug system is a distraction. It wastes engineering resources on the illusion of absolute safety. True software excellence happens when teams respect the natural limits of testing. They embrace risk analysis, identify failure points early, and use every runtime error to fortify the architecture of their process.